Welcome. Tonight you are here, and that is enough. Wherever you are listening from, your bed, a quiet room, somewhere far from the day's noise, let your shoulders drop a little and let your breath find its own slower rhythm. There is no place to be tonight and nothing more to do. This is the Circadian Institute, where each night we travel somewhere ancient and quiet, somewhere too large for words, and let the slow rhythms of the cosmos carry our minds towards sleep. Tonight, our destination is a nebula, one of the great star nurseries scattered across the dark. If you find this calming voice helpful, please subscribe. The light from these clouds has been traveling for a very long time before reaching us. Some of it left its source before the first humans walked. Some of it left before there were forests, before there were oceans of the shape we now know. The photons that paint a nebula's colors in our telescopes have been crossing the dark alone for ages. Tonight they have arrived. Inside a nebula, gravity works very gently and very slowly. A wisp of gas drifts a little closer to another wisp. Over thousands of years they merge. Over millions of years, the merging gathers into denser knots. Eventually, somewhere inside the cloud, a knot becomes heavy enough that it begins to glow with its own warmth. A new star has begun, quietly, with no one there to see. If your mind drifts during this video, that is welcome. You do not need to follow every detail. The voice will keep going, the colors will keep unfolding, the universe will keep being patient. You are allowed to fall asleep early. You are allowed to stay awake and watch. There is no wrong way to be here tonight. So let yourself settle in. Adjust your blanket if you need to. Soften your breathing. The cosmic quiet has been waiting for a long time, and it is ready to receive you. We will begin by drifting outward, past the moon, past the planets, past the edges of our solar system into the wide, dark spaces where the nebulae live. Let us begin with the simplest possible description. A nebula is a region of space where gas and dust have gathered. The word itself comes from Latin, meaning cloud or mist. For most of human history, that is exactly what these objects look like. Soft smudges of light among the sharper points of stars. The truth of what they are has only been understood within the last few generations. The most of a nebula is hydrogen. This is the lightest, simplest, most ancient element in the universe. The hydrogen in any nebula tonight has existed since the early universe. Only a few 100,000 years after the great beginning, it has drifted and gathered and dispersed and gathered again for billions of years. Now it forms part of the cloud you're watching. Mixed with the hydrogen is some helium and a small fraction of heavier elements: carbon, oxygen, nitrogen, silicon, iron. These heavier atoms were made inside stars that lived and died long before our sun was born. They were exhaled into the cloud when those earlier stars reached the end of their lives. A nebula carries inside it the memory of all those finished suns. There is also dust. Cosmic dust is not like household dust. It is much finer, made of tiny grains of silicate and carbon, often coated in ice. Each grain is smaller than the smoke from a candle, yet when you gather enough of them across light years of space, they become thick enough to block the light of stars behind them. Some nebulae are visible only because of their dust. The size of a nebula is hard to picture from inside our human scale. The Orion Nebula spans roughly 24 light-years across. That means a beam of light traveling at the fastest possible speed would take 24 years to cross it from edge to edge. The Tarantula Nebula in a neighboring galaxy stretches nearly 1,000 light-years. These are not landscapes, they are entire territories of space. Despite their enormous size, nebulae are remarkably empty by Earth standards. The thickest parts of a nebula contain only a few thousand atoms per cubic centimeter. The best vacuum we can create in our laboratories is denser than this by far. A nebula is mostly empty space with a sparse, glowing breath of matter spread very thinly across vast distances. And yet, because nebulae are so vast, the total mass inside one of them is enormous. The Orion Nebula contains as much material as roughly 2,000 suns. The largest molecular clouds, where many nebulae are born, can hold the mass of 1,000,000 suns in their depths. From this immense, slow reservoir, future stars are gradually drawn together by gravity. To find a nebula in the night sky, you generally look toward the disk of the Milky Way. Our galaxy is shaped like a flattened spiral, and almost all of its star-forming clouds lie within that disk. When you look up at the band of soft light called the Milky Way, you are looking edge-on into a region thick with both stars and the clouds from which more stars will come. There are nebulae in other galaxies as well, although they are too distant for our eyes alone. We can see the largest of them through telescopes, the Great Tarantula Nebula in the Large Magellanic Cloud, or 30 Doradus, with its violent and beautiful star formation. Distance does not change a nebula's nature. It only softens it, makes it smaller, lets us hold it in our gaze. The discovery that nebulae exist as separate objects came slowly across many centuries. Early astronomers with simple telescopes saw fuzzy patches and called them all by one name. The French observer Charles Messier listed many of them in the 1700s simply to avoid mistaking them for comets. He never imagined what they would later turn out to be. It was not until larger telescopes and the techniques of spectroscopy arrived that astronomers could begin to read the chemistry of these clouds. By passing nebula light through a prism, they discovered the unmistakable fingerprints of hydrogen, oxygen, and other elements. The clouds were not just luminous fog, they were vast chemistry, suspended in the dark. With photography, nebulae began to reveal their true colors. Long exposures captured the soft reds and greens and blues that the human eye cannot quite gather on its own. Photographs from the late 1800s onward turned what had been fuzzy gray smudges into vast, painterly landscapes of light. We had been looking at art all along. Then came the great space-based telescopes, the Hubble, the Spitzer, the Chandra, and most recently the James Webb. From above the smearing fog of our own atmosphere, they have shown us nebulae in detail no one before us has ever seen. Each new image is a kind of gift across deep time, slow generations of light meeting our newly opened eyes. Nebulae move, although you would never see it. The gas inside them drifts at speeds of perhaps 10 or 20 kilometers per second. That sounds fast, until you remember the size of these clouds. Across a nebula, thousands of light years wide, those speeds amount to almost no visible motion at all over a human lifetime. To us, they are perfectly still. In another sense, however, nebulae are violent places. Inside them, shock waves from young stars carve cavities and pillars. Magnetic fields squeeze and twist the gas. Radiation lights up some regions while ionizing others. From within a nebula, much is happening. From outside, all of it appears as a single soft glow, calm to the casual eye. Some nebulae shine because they contain hot young stars whose ultraviolet light excites the surrounding gas, making it glow. Others shine because nearby stars illuminate the dust, scattering blue light back to our eyes. Others are dark, visible only as silhouettes against brighter backgrounds. The reason a nebula is visible at all tells us something about what is inside it. Among the famous nebulae are some you may already have heard of. The Orion Nebula, the Eagle Nebula with its pillars of creation, the Lagoon, the Trifid, the Crab, the Veil. Each has its own personality, its own colors, its own story of how it came to be. Tonight we will visit several of them in their own slow time. Nebulae do not last forever. Over timescales of millions to tens of millions of years, the clouds that birth stars are gradually consumed or dispersed. The new stars they produce drift away. The leftover gas is pushed outward by radiation. What remains slowly fades into the wider thinness of interstellar space, waiting for some future event to gather it again. And so, in their long way, nebulae are also moments. They are temporary gatherings of cosmic material, bright pauses in the great drift of matter through the galaxy. We happen to live in a moment when many of them are visible to us, lit and shining. There may be future ages when fewer remain. There may be past ages when more existed. Every atom in your body, every grain of calcium in your bones, every iron atom in your blood, every flicker of carbon in your nerves was once part of a cloud of cosmic material. At one point in deep history, you were a nebula. So tonight, when we look at these clouds, we are also looking, in a sense, at our own distant ancestry. This is the simplest, gentlest fact about a nebula. It is matter, drifting and gathering in no particular hurry. From it, stars are born, and to it, eventually stars return. We are momentarily in between, neither cloud nor remnant, but the brief warm light somewhere in the middle of the cycle. Tonight we are visiting where we came from. The cataloging of nebulae has its own quiet history. Charles Messier, in his original 18th century list, included 110 objects of various kinds. Later, the new General Catalog and the Index Catalog added thousands more. The Sharpless Catalog focused specifically on emission regions in the northern sky. Each nebula now carries multiple names. Its Messier number, its NGC entry, its Sharpless designation. The same patient cloud, seen from different scientific eras. If you could somehow visit the inside of a nebula, you would not actually see anything dramatic. The gas is so thinly spread that an observer in the middle of a nebula would simply see ordinary stars on every side, with perhaps a very faint diffuse glow if the surrounding gas were excited. Light pollution from our cities and roads has made nebula observation increasingly difficult from inhabited areas. Even from a darker site, the unaided eye can see only the brightest few: the Orion Nebula, the Lagoon, the Andromeda Companion. Most others require telescopes or photography to reveal. In the patient dark of remote skies, however, many nebulae return as soft glowing presences much closer to what our ancestors knew. For most of human history, nebulae were sometimes mistaken for comets. The fuzzy patches look similar in early small telescopes, especially when seen briefly. Charles Messier compiled his catalog precisely so that future comet hunters would not be fooled. He listed each known nebula carefully so that anyone who saw a fuzzy spot in that location would know it was a permanent fixture of the sky, not a wanderer to be tracked. The discovery in the early 20th century that some so-called nebulae were actually entire other galaxies was one of the great revelations of human knowledge. Before Edwin Hubble's careful measurements in 1923, what we now call the Andromeda Galaxy was simply known as the Andromeda Nebula. The realization that it lay far beyond our own Milky Way reshaped our idea of the universe overnight and quietly changed the meaning of the word nebula. Now that we have a sense of what a nebula is, let us drift toward how a star actually begins inside one. The process is so slow it almost cannot be called an event. It is more like a posture that gas slowly settles into. We will follow that settling very gently in the next chapter. Inside a quiet stretch of nebula, somewhere among the wide drifting hydrogen, gravity begins its work. Gravity is not a fast force. In a thinly spread cloud, its pull on any one atom is almost nothing. Yet across millions of years, those tiny pulls add up. Slowly, the cloud begins to gather. The story of every star starts with this almost invisible gathering. The gathering tends to begin in the densest pockets of a molecular cloud. These pockets may form because of a passing shock wave from a nearby supernova or from the spiral arm of the galaxy sweeping through the gas. Sometimes simply random fluctuations in density are enough. Whatever begins it, once a region is dense enough, gravity takes over with patience. As the gas gathers, it must lose energy. If it could not, the gas would simply heat up, and the heat would push back against gravity. But the dust and molecules in the cloud allow it to radiate heat away as infrared light. The cloud slowly cools, and the cooling allows it to contract. This is the great slow handshake between heat and gravity. Eventually, the contracting region becomes opaque to its own radiation. Heat can no longer escape easily, and the temperature of the core begins to climb. The pressure rises, the gas, no longer cool, presses back against gravity. A balance is reached, almost. The dense core, now warm, becomes what astronomers call a protostar. A protostar is not yet a star. It glows faintly, but only from the heat of its own contraction. It has not yet ignited its inner fuel. The protostar phase can last hundreds of thousands of years for a star like our Sun. For a smaller star, it can last much longer. There is no rush in the universe to make a star. Around the young protostar, a flat disk of leftover gas and dust forms. This disk contains the raw material of any planets that may eventually orbit the new star. Even before the star is ignited, the planets are quietly being assembled, grain by grain, in the disk's warm interior. Time, here, must be measured in millions of years. From the first gravitational gathering, through the protostar phase, through the slow ignition of nuclear fusion at the core, the entire process can stretch across 10 to 50 million years. By comparison, the entire span of human civilization fits inside a small fraction of that. Stars do not hurry to be born. As the protostar contracts, it begins to spin faster. The conservation of angular momentum, the same principle that makes a spinning skater accelerate when she pulls in her arms, applies to gas as well. The young star spins, the disk around it spins. Some of that rotation eventually launches outward as twin jets above and below the disk. These jets are called bipolar outflows. They can stretch for light years above and below the disk, glowing where they slam into the surrounding gas. Where they collide with cold cloud material, they create bright knots called Herbig-Haro objects. These knots are some of the most striking signs that a new star is being born. Most of the protostar phase is hidden from view. The dust around the young star blocks visible light entirely. From outside, an observer with ordinary telescopes would see only a dark patch in the cloud. The new star's birth is taking place in the kind of quiet that resists witness. Only infrared and radio telescopes can peer through the obscuring dust. Infrared telescopes have given us our best views of star formation. From space, instruments like Spitzer and now the James Webb peer through the dust at the warmth within. They show us bright young stars cradled inside their birth clouds, surrounded by glowing rings and elongated jets. The hidden process becomes briefly visible. The stars rarely form alone. Inside a single molecular cloud, dozens to hundreds of stars may form over the course of a few million years. They form together in clusters, sharing the same chemical heritage. The Pleiades, visible to your naked eye on a clear night, is such a cluster. So is the trapezium at the heart of the Orion Nebula. Stars form in clusters because the conditions that gather one part of a cloud often gather neighboring parts as well. A passing shock wave compresses a wide region, not just a single point. The result is a cooperative birth. Many young stars share their first few million years close together before the slow work of orbital drift carries them apart. Eventually, when the contracting protostar is dense and hot enough at its core, hydrogen begins to fuse into helium. This is the moment a star truly becomes a star. The fusion releases enormous energy, which pushes outward against gravity, balancing the inward pull. A stable star is born. From this moment, it can shine for millions to billions of years. For a star like our Sun, the first burst of hydrogen fusion may have occurred about 4.5 billion years ago. Deep inside a now long-vanished cloud, we can no longer see that cloud. The other stars that formed alongside our Sun have drifted across the galaxy. Yet the spark from that ignition has been carrying our world forward ever since. Once a young star ignites, its radiation begins to push back against the surrounding gas. Solar wind streams outward, sweeping nearby material aside. Powerful ultraviolet light ionizes the cloud, heating it and driving it away. Slowly, the new star carves out a cavity around itself. The womb is dispersed, gently, by the very fire it was meant to nurture. This is why we can see so many young stars surrounded by glowing pink rims. The ultraviolet light of the new star excites the hydrogen at the edge of the cloud, making it shine. The pink halo is the cloud being slowly cleared away. Within a few million years, the surroundings are mostly gone, and the star stands alone. After the star emerges from its cloud, it begins its long, stable phase. For a star like our Sun, that stable phase lasts about 10 billion years. Most of a star's life is calm. Most of a star's life is steady. Most of a star's life is the patient burning of hydrogen deep in the core with no drama and no haste. Throughout the galaxy, this same slow process is happening at this very moment. In hidden corners of the Orion Nebula, in the depths of the Eagle, in the quiet recesses of the Carina Nebula, new stars are gathering and igniting and finding their first stable balance. None of them know we are watching. None of them need our witness to begin. But on Earth, all of this took place inside a cloud that no longer exists. around 4.5 billion years ago. The Sun's birth siblings have long since drifted into the wider galaxy. The cloud itself was slowly cleared away. Only a few hints remain in the form of certain isotopes preserved in ancient meteorites. Yet without that vanished cloud, none of us would be here. So when you look at a nebula tonight, remember that you're looking at a place where this same slow miracle is unfolding. New stars are coming into being, patiently, with no urgency, with the same quiet grace that brought our own sun into existence. The universe has been making stars for over 13 billion years, and it is still making them tonight. Magnetic fields play an underappreciated role in star formation. Throughout a molecular cloud, faint magnetic fields thread through the gas, providing a kind of internal scaffolding. They can resist the contraction of gravity, slowing the formation of new stars. But only when a region of cloud has gathered enough mass to overcome both gas pressure and magnetic support does the slow collapse truly begin in earnest. Patience and resistance balanced for ages. T Tauri stars are very young stars that have just emerged from their birth clouds. They are still contracting toward their final shape, still surrounded by remnants of their planet-forming disks, still bursting with fluctuations in brightness as their final stable structure settles into place. They are named after the variable star T Tauri itself in the constellation Taurus near the Hyades cluster, the original example of this restless youthful phase. Astronomers measure star formation rates by counting young massive stars, by surveying glowing emission regions, and by using infrared and submillimeter observations to look directly at the warmth of forming stars. Different methods sometimes give different answers. The most active star-forming galaxies in the universe convert thousands of solar masses of gas into new stars every year. Our own Milky Way is much more modest, producing only a few solar masses of new stars each year. Inside molecular clouds, gas does not flow smoothly. It is turbulent, full of swirls and eddies on every scale from light years down to small fractions of a light year. The turbulence stirs the cloud and prevents it from collapsing all at once. Star formation happens only in those quieter regions where the turbulence has temporarily settled, allowing gravity to take hold without competition. The cloud breathes through its turbulence. Our own sun was born somewhere in the Milky Way about 4.5 billion years ago in a cloud now long dispersed. The siblings of the sun, born from the same cloud, have drifted across many parts of the galaxy in the time since. Some may still be relatively close, others may be on the opposite side of the disk. Identifying the sun's birth siblings is one of the open puzzles in modern stellar astronomy, a slow, scattered family. Now that we have followed the slow birth of a single star, let us turn toward a particular and famous place where this birth is happening on a grand scale. The pillars of the Eagle Nebula are some of the most visited landmarks in cosmic photography. Let us drift toward them now, gently and without hurry. In the constellation Serpens, about 6,500 light-years from Earth, lies the Eagle Nebula. It is part of a larger star-forming region known as Messier 16. Within this nebula are some of the most photographed structures in all of astronomy, the towering columns of gas and dust that we have come to call the pillars of creation. The pillars rise from the nebula's interior like immense, slow towers, dark against the brightness behind them. The tallest of them stretches about 4 light-years from base to tip. To imagine that picture light itself traveling at the fastest possible speed, taking 4 entire years to climb from the bottom of the column to the top. They were first imaged in detail in 1995 by the Hubble Space Telescope. The photograph that resulted became one of the most famous images ever taken of the cosmos. It hung in classrooms and offices around the world. Many people first encountered the idea of a nebula through this single, quiet picture of 3 slow towers. Although the pillars look solid in photographs, they are not. They are made of cold molecular hydrogen and dust, much denser than the surrounding cloud, but still less dense than air on Earth. If you could somehow stand on the surface of one, you would pass right through it. The shape is more like a long-lasting fog than any kind of structure. Nearby, just above the pillars, lies a cluster of hot young stars known as NGC 6611. These stars are massive, blue, and intensely bright. They emit enormous amounts of ultraviolet radiation, and that radiation is what is slowly carving the surrounding cloud into the pillar shapes we see. The process by which a nebula develops pillars is called photoevaporation. The intense ultraviolet light from nearby young stars heats the gas at the cloud's surface, causing it to expand and stream away. Wherever the cloud is denser, it resists this erosion longer. Wherever it is thinner, it is stripped away first. Over time, the dense regions remain, standing tall like pillars after the rest has eroded. At the tips of the pillars, you can sometimes see small dark knots. These are called evaporating gaseous globules, or AGGs. Each one is a particularly dense pocket within the pillar, slowly resisting the surrounding erosion. Inside some of these AGs, new stars may already be forming. Each AG is a quiet experiment in gravity and time. The pillars of creation are not eternal. They are being slowly eroded year after year by the relentless light of those young blue stars. In another few 100,000 years, they will be gone. From a human perspective, that is a long time. From the perspective of the universe, it is barely a moment. The pillars are, in cosmic terms, brief. There is another, stranger thing to consider. The pillars of creation we see in photographs are about 6,500 light years away. The light from them takes that long to reach us. So when you look at the Hubble image, you are seeing the pillars as they were 6,500 years ago. As you look, you cannot know whether they still exist now. In fact, some astronomers have suggested that a nearby supernova may already have destroyed the pillars in their own present time. Infrared observations have detected what appears to be a hot expanding shock wave near the pillar region. By the time we receive light showing whether the pillars have survived or been destroyed, perhaps another 1,000 years will pass. This kind of uncertainty is built into all astronomy. We never see the universe as it is now. We always see it as it was however many years ago the light first set out. The cosmos shows us only its past. Whatever it is doing in this moment, we will not know about for a long time, and that in its own way is calming. In 2014, the Hubble revisited the pillars. With improved instruments, it captured them in greater detail than the original 1995 image. The new pictures showed the same towering shapes, the same EGGs at the tips, but with sharper edges and more subtle colors. The pillars had hardly changed in human time. Of course they had not. Then in 2022, the James Webb Space Telescope turned its infrared eye toward the pillars. The Webb image revealed something the Hubble could not: the young stars hidden inside the columns themselves. Where the visible light Hubble saw only opaque towers, the Webb saw soft red points of light embedded throughout. the new stars that the pillars had been quietly nursing all along. The web pictures also showed wisps of gas streaming outward from the pillar tips, as if the towers were softly exhaling. They revealed the deep texture of the dust, like the fibers of an old curtain. They showed in greater clarity than ever before that even the most still-seeming objects in space are full of quiet motion. The pillars are not the only such structures in the universe. The Orion Nebula contains its own dramatic columns, including the strange mystic mountain, a cosmic outcrop nearly 3 light-years tall, with twin jets blasting from a young star embedded near its top. Wherever there are bright young stars eating into a dense molecular cloud, structures like these can form. The Cone Nebula in the constellation Monoceros contains a single great pillar that resembles a quiet horn pointing into space. The Sol Nebula has its own elongated columns. The North America Nebula, near the bright star Deneb, hides multiple pillar-like ridges in its dustier corners. The pillar shape is, it turns out, quite common throughout the galaxy. There is something deeply human about the way we name and remember these structures. The pillars of creation, the mystic mountain, the eagle, the cone, the horsehead. We give them names that turn cosmic shapes into something familiar, something we can almost reach toward. The universe does not know our names. We use them anyway, gently. Standing in some of the older photographs, looking at the pillars, you can almost feel a stillness, although you know intellectually that the towers are slowly burning away under ultraviolet light. The contradiction is not a problem. The universe holds both at once, appearance of stillness, reality of slow change. In the contradiction, there is calm. If you ever doubt that beauty exists for its own sake, remember the pillars. No one was ever supposed to see them. They formed in deep space billions of years ago, far from any conceivable observer. They will be gone in a few 100,000 years, yet here they stand, briefly, brilliantly, in their improbable shape. We did nothing to deserve them, and they appeared anyway. So tonight, while you rest, the pillars are still doing what they have always done. New stars are quietly gathering inside their eggs. Old gas is slowly being stripped away by ultraviolet light from young blue stars. The whole structure is breathing, very slowly, in a rhythm of erosion and rebirth that has nothing to do with us. There are countless other star-forming columns throughout the Milky Way, most of them never to be photographed by any telescope humans build. Each is a brief, magnificent slow-motion event. Each is a place where matter is patiently arranging itself into the shape of stars. Each is in some quiet way a creation. Behind every famous Hubble image are quiet teams of engineers, scientists, and artists. The original raw images are usually black and white grayscale exposures taken through narrow filters at specific wavelengths. Choosing how to combine those exposures into a final color photograph is partly a scientific decision and partly an artistic one. The final images are real, but they are also interpretations, gentle translations from raw data into something the human eye can love. The colors in Hubble images of the pillars are usually false, in the sense that they do not match what the human eye would see directly. Often they follow what astronomers call the Hubble palette, where sulfur emission is shown as red, hydrogen as green, and oxygen as blue. The result is not a deception. It is a way of revealing chemistry that the eye alone could never detect, a kind of color hearing for the cosmos. When the pillars are observed in X-rays, almost nothing visible appears. Their cold gas does not emit X-rays, but around them, hot gas from young stars and supernova remnants does shine brightly. By comparing X-ray and visible images, astronomers can map both the cool pillar interior and the hot environment that is gradually eroding it. Different wavelengths show different worlds, and only their combination tells the full, slow story. Not every AG inside a pillar successfully forms a star. Some are too small or too loosely bound, and they evaporate completely before gravity can finish its work. From the perspective of a single AGG, the outcome is uncertain. Some will become stars, others will simply return their gas to the wider cloud. Each egg is an experiment in the slow patience of cosmic formation, with no certainty of any particular ending. There is something quietly philosophical about looking at the pillars. They are immense, ancient, and beautiful, and yet they are also temporary. They have lasted long enough for humans to evolve, build telescopes, and photograph them. They will not last so much longer. Their existence overlaps with ours by a slender thread of cosmic time. We are seeing them, and they are passing both at once, both true. Now we have visited some of the most famous towers in the sky. Let us drift toward the brighter, more open kinds of nebulae, the great glowing emission clouds where hydrogen itself shines with its own borrowed light. The Orion Nebula awaits us in the next chapter in its own slow time. Some nebulae shine with their own light, not their own internal fire, but the light of nearby young stars exciting the gas within them. These are called Emission Nebulae. They are some of the brightest, most colorful, most photographed objects in the sky. Tonight we will spend some patient time among them. The most famous emission nebula in our sky is the Orion Nebula, also known as Messier 42. It lies about 1,300 light-years from Earth in the great constellation of Orion. On a clear winter night, you can see it with your naked eye as a soft blur in the middle of the hunter's sword. Through binoculars, it becomes a misty cloud. Through a telescope, it becomes a wonder. The Orion Nebula is roughly 24 light-years across and contains the mass of about 2,000 suns. Inside it, hundreds of new stars are being born at this very moment. It is the closest large region of active star formation to Earth, and as such, one of the most thoroughly studied objects in modern astronomy. At the heart of the Orion Nebula sits a small, tight cluster of brilliant young stars known as the trapezium. There are 4 bright members of this cluster easily visible through telescopes, and many more fainter stars surrounding them. The largest trapezium star is 40 times the mass of our Sun and tens of thousands of times more luminous. These massive young stars are emitting enormous quantities of ultraviolet radiation. The ultraviolet photons strip electrons from the hydrogen atoms in the surrounding gas. When those electrons later recombine with their hydrogen nuclei, they emit photons of specific wavelengths, including the deep red glow we associate with hydrogen alpha emission. This is why emission nebulae are red. The dominant glow is from hydrogen alpha, a particular wavelength of red light produced when an electron returns to its second lowest energy state in a hydrogen atom. Vast clouds of glowing hydrogen, ionized by young blue stars, give emission nebulae their characteristic deep red color. Beyond hydrogen, other elements contribute their own colors. Oxygen ions emit a soft green light when their electrons return to specific energy states. Sulfur ions emit a deeper red. Nitrogen, helium, and other trace elements add their own subtle hues. Together, these glows produce the painterly palettes we see in deep nebula photographs. Astronomers can identify the chemical composition of a nebula by passing its light through a prism or grating. The resulting spectrum shows narrow, bright lines at specific wavelengths, each corresponding to a particular element or ion. From these lines, we can read the chemistry of clouds thousands of light years away. The early astronomers who first studied nebula spectra found something puzzling. Some of the brightest emission lines did not match any known element. For decades, they were attributed to a mysterious substance called nebulium. Only later was it realized that those lines came from oxygen and other common elements, but in conditions impossible to reproduce on Earth. In the rarefied vacuum of a nebula, atoms can sit undisturbed for very long times. They can release certain types of radiation that would normally be smothered by collisions in any denser gas. These so-called forbidden lines became, for nebula astronomers, some of the most informative tools available. The vacuum permits a chemistry the laboratory cannot. Beyond the Orion Nebula, there are many other beautiful emission regions. The Lagoon Nebula, Messier 8, lies in the constellation Sagittarius, about 4,000 light-years away. It is large enough to be seen with binoculars even in moderately dark skies. Its central region contains a pair of bright young stars actively carving the gas around them. Near the lagoon in the same patch of sky lies the Trifid Nebula Messier 20. Its name comes from the dark dust lanes that divide the bright emission region into 3 lobes. The Trifid is unusual because it shows both emission and reflection nebula characteristics in one body, bright pink hydrogen alongside softer blue dust scattering. Far in the southern sky, in the constellation Carina, lies one of the largest and most spectacular emission nebulae in our galaxy, the Carina Nebula. It spans more than 300 light-years and contains the unstable, supermassive star Eta Carina, which has been threatening to go supernova for over a century. The Carina region is a place of slow drama. In northern skies, the North America Nebula in the constellation Cygnus takes the recognizable shape of the North American continent on its eastern side. The Pelican Nebula sits beside it, divided from it by a dust lane. Together they form a single huge complex of glowing hydrogen along the line of the Milky Way's bright summer band. Cataloging emission nebulae has been a long process. The Sharpless Catalog, compiled in the 1950s, listed over 300 such regions in the northern sky. The RCW Catalog cataloged hundreds more in the southern sky. Modern surveys at infrared and radio wavelengths continue to reveal additional faint emission regions throughout the galaxy. Some emission nebulae are so large and so close that their structure is seen unfolding across our entire sky. The Gum Nebula, named after the Australian astronomer Colin Gum, may be the closest large emission region to Earth, lying only about 1,300 light-years away and spanning 40 degrees across the southern sky. Stars within an emission nebula not only light the surrounding gas, they also push it. Their stellar winds carve out cavities. Their ultraviolet light heats and ionizes whatever is closest, while their radiation pressure pushes the gas outward. Over millions of years, the original cloud is reshaped into ever more elaborate structures. Around the boundaries of emission regions where the ionized gas meets the colder cloud beyond, an ionization front forms. On one side of the front, the gas is hot, glowing, and thin. On the other side, the gas is cold, dense, and dark. The front itself migrates outward, slowly chewing into the cold cloud as the young stars continue to shine. These ionization fronts are some of the most beautiful features in detailed nebula images. They appear as bright curving edges, glowing in red and orange, with dark dust beyond them. They look like the slow shores of a luminous tide eating into a quiet continent. From the perspective of the cloud, they are a kind of weather. Without massive young stars to provide the ultraviolet light, there would be no emission nebulae. The shorter the lifetime of the parent stars, the shorter the lifetime of the surrounding glow. Massive stars live only a few million years, so emission nebulae are short-lived in cosmic terms, bright moments lit by brief, intense stars. After the massive stars die, often in supernovae, the gas they once illuminated returns to darkness. The emission nebula fades. The cooler dust regions that survive become the seeds of future star formation. The cycle continues in its slow, patient way even after the bright glow is gone. The Rosette Nebula, in the constellation Monoceros, takes the lovely shape of a cosmic flower. Its central cluster of hot young stars has cleared out a wide cavity, and the surrounding gas glows in deep red around it. The rosette is large enough to be a popular target for amateur astrophotographers, and its symmetry makes it one of the more recognizable emission nebulae in the sky. A flower the width of 100 light years, blooming patiently. In the constellation Cassiopeia lie the Heart and Soul Nebulae, two large adjacent emission regions that have, by coincidence of shape, acquired their evocative names. Together they span a large portion of the autumn sky. Inside both, young stars are actively forming, and the pink hydrogen alpha glow extends across hundreds of light years from end to end. The shapes are illusion, but the chemistry behind them is entirely real. Modern astrophotographers often use narrowband filters to image emission nebulae. These filters allow only the specific wavelengths of hydrogen, oxygen, or sulfur emission to pass through. The result is images of remarkable contrast, where the nebula's structure stands out clearly from the surrounding sky. Even in light-polluted suburbs, narrowband imaging can reveal nebulae that would otherwise be invisible to the naked eye. The combination of sulfur, hydrogen, and oxygen emissions, mapped to red, green, and blue, produces what astronomers call the SHOW or Hubble palette. Many of the most famous nebula images you have seen use this palette. The colors are scientifically meaningful, they encode actual chemistry, but they are not what the eye would see. They are a translation from the chemistry of cosmos into the language of vision. Emission nebulae also speak in radio waves. The hot ionized hydrogen within them emits a faint continuous radio signal, and certain molecules within their cooler edges emit at specific radio frequencies. By tuning radio telescopes to those signals, astronomers can map the structure and temperature of an emission nebula in detail invisible to the eye. The cosmos murmurs in many languages at once. Now we have wandered through the bright, glowing emission regions. Let us turn next to the more quietly luminous nebulae, the reflection nebulae, where the light is borrowed rather than created, and the colors are softer and bluer. The next chapter takes us toward the Pleiades. Not all nebulae glow on their own. Some shine because they are illuminated by nearby stars, with the light bouncing softly off countless particles of cosmic dust. These are called reflection nebulae. They are quieter than emission nebulae, more subtle, and almost always blue. Tonight we will spend some time with them. The most famous reflection nebula visible from Earth is the dust cloud surrounding the Pleiades star cluster. The Pleiades, also known as the Seven Sisters, is one of the most easily recognized objects in the night sky. On a clear winter night, you can see it as a small, tight grouping of stars in the constellation Taurus. The Pleiades cluster lies about 444 light-years from Earth. It contains over 1,000 stars, although only the brightest are visible without a telescope. The cluster's hot blue stars are passing through a region of cold cosmic dust. The dust scatters the starlight back to our eyes, producing the soft blue glow we see in long exposure photographs. This blue color happens for the same reason the daytime sky on Earth is blue. Particles of dust, like air molecules, scatter shorter wavelengths of light more efficiently than longer ones. Blue light bounces in many directions, red light continues mostly straight. So when starlight passes through a dust cloud, the blue is scattered back toward us and the cloud appears blue. In contrast, emission nebulae get their color from glowing gas, mostly hydrogen alpha. Reflection nebulae get their color from scattered starlight. Even when both kinds of nebulae are present in the same region, the difference is visible. Emission glows in pinks and reds, reflection glows in blues. Many famous nebulae contain both processes side by side. The Trifid Nebula, which we mentioned briefly in the previous chapter, contains both emission and reflection regions. Its central area is a bright pink emission cloud divided by dark dust lanes. Above it, a softer blue reflection nebula gently scatters the light of nearby young stars. The Trifid is a small lesson in nebula chemistry, all in one frame. Another well-known reflection nebula is the Witchhead Nebula, near the bright star Rigel in the constellation Orion. The cloud takes the eerie shape of a profile silhouette, lit blue by Rigel's intense radiation. Despite the strange name and shape, the Witchhead is simply a quiet patch of cosmic dust illuminated by a bright neighbor. In the constellation Cepheus lies the beautiful Iris Nebula, NGC 7223. It surrounds a bright young star with a soft, intricate blue glow. Long exposure images of the iris show delicate filaments of dust, intricate as the petals of its namesake flower, all gently illuminated by the central star. In the constellation Orion, near the famous Horsehead, there is also the small but beautiful reflection nebula known as the Cocoon Nebula. It is a tight blue cloud centered on a young star that has carved a small bubble in the surrounding dark cloud. The cocoon is exactly what it sounds like, a quiet wrapping of light. Reflection nebulae have been useful tools for studying interstellar dust. By analyzing the scattered light, astronomers can deduce the size, composition, and density of the dust grains in a cloud. Different grain sizes scatter light differently. The shape of the scattered spectrum tells us much about the cosmic dust we cannot otherwise reach. Cosmic dust grains are typically smaller than a wavelength of visible light. They are composed of silicate minerals, carbonaceous compounds, and ices. They form in the cool atmospheres of older stars and are scattered into space when those stars shed their outer layers. The dust we see today has been recycled across many stellar generations. In some cases, a star is not embedded in its own birth cloud, but is simply passing through one. The bright star that lights up the Iris Nebula, for instance, was not born in the cloud it now illuminates. It is a chance traveler, briefly making the surrounding dust glow as it passes through. In a few million years it will move on, and the iris will quiet again. These chance encounters are especially common in regions where many stars are moving through dust-rich areas of the galaxy. The result is a sky full of small, soft reflection nebulae, each lit by whichever star happens to be passing near it. From our perspective, they are quiet, illuminated moments scattered across the dark. Reflection nebulae are particularly difficult to photograph well. They are usually faint, requiring long exposures, and they are easily overwhelmed by the brighter stars within them. Astrophotographers learn over time the patient art of revealing the soft blue halos around bright stars without burning out the central regions. The Hubble Space Telescope produced beautiful images of the Pleiades and its surrounding reflection nebula. The photographs show the dust as a delicate web of fine filaments, each one curving and intersecting the others. The blue light shimmers across them like an old silk fabric. The result is some of the gentlest cosmic photography ever made. It is worth pausing on the simple beauty of these images. Inside a great cloud of cold dust, light from distant stars has scattered, and that scattered light has, after centuries of travel, reached our telescopes. We have arranged to receive it and to share it. Tonight that light is reaching you, gently, after its very long journey. The Pleiades has been observed and named by cultures around the world for thousands of years. The Greeks called them the Seven Sisters, daughters of Atlas. The Aboriginal Australians have stories of seven sisters fleeing across the sky. The Maori, the Inuit, the Lakota, the Japanese, the Hindus, the Persians, almost every people that has watched the night sky has noticed and named these stars. And in many of those cultures, the cluster has been associated with the changing of seasons, with planting and harvest, with the slow turning of the year. The Pleiades rise and set at predictable times. They have served as a calendar in the sky for as long as humans have been farmers. Their soft blue halo has been with us a long time. The dust around the Pleiades is not, in fact, the original cloud that formed the cluster itself. The cluster is moving through unrelated cold gas. The two are passing through each other temporarily in a chance meeting of moving star and stationary cloud. In about another 20,000 years, the Pleiades will have moved on and the dust will quiet. This temporary meeting reminds us that nothing in the cosmos is fixed. Stars move, clouds drift. Even the most familiar shapes in our night sky are slowly rearranging themselves on timescales we cannot perceive. The constellations our ancestors saw are not the same as the ones our descendants will see. The sky is always quietly in motion. In a sense, every night you look up, you're looking at a sky that has just slightly changed since the night before. The change is too small for the eye to catch in any human lifespan, but over the deep time scales of cosmic history, every star and every nebula is on its own slow journey, finding its own slow place. Hubble's variable nebula in the constellation Monoceros is an unusual reflection nebula whose appearance changes from year to year. The young variable star R Monocerotis at its center fluctuates in brightness, sometimes obscured by passing dust, sometimes revealed, and the surrounding cloud brightens or dims along with it. It was the first object ever photographed by the Hubble Space Telescope, fittingly named for the same astronomer it honors. Messier 78 in Orion is one of the brightest reflection nebulae in the sky. Two bright young stars at its center light up the surrounding cloud in soft blue, with delicate dust filaments extending outward. M78 lies near the Horsehead Nebula in the same general molecular cloud complex. The two famous nebulae are essentially neighbors in the constellation, separated only by quiet stretches of cold gas. For many years, astronomers believed that the dust around the Pleiades was the original cloud from which the cluster had formed. Newer measurements have shown that this is not the case. The cluster is simply moving through an unrelated dust cloud, briefly illuminating it. The encounter is temporary. In about another 20,000 years, the Pleiades will have moved on and the dust will quiet again into the dark. The light from a reflection nebula is polarized. When light from a star scatters off dust grains, the scattered light vibrates preferentially in certain directions. By measuring this polarization, astronomers can study the size, shape, and even the alignment of the dust grains. The tiny particles in a cosmic cloud in this way reveal themselves at a microscopic level from far away across many light years. When you look at a long exposure photograph of a reflection nebula, your eye sometimes perceives a strange three-dimensional depth. The dust appears to wrap around the bright stars, throwing them into sculptural relief. This is largely an optical illusion produced by the way scattering creates soft halos. Yet the illusion is true to something real. The dust really is around the star, in three actual dimensions, just not as our eyes suggest. And now we have lingered with the soft blue reflection nebulae and the cosmic dust they reveal. Next, let us turn to the darkest and quietest nebulae of all, the cold, dust-rich clouds that produce no light of their own and reveal themselves only as silhouettes. The next chapter takes us to the Horsehead. There is another kind of nebula, less famous than the bright, glowing ones, but just as important in the slow life of the galaxy. These are the dark nebulae, clouds of cold gas and dust so thick that they block the light of stars behind them. Tonight, we will spend some time among these quiet shadows. The most famous dark nebula is the Horsehead, located in the constellation Orion, about 1,500 light-years from Earth. It takes its name from the unmistakable shape of a horse's head and neck, dark against the bright pink emission cloud behind it. The Horsehead is one of the most photographed objects in modern astronomy. In catalogs, the Horsehead is known as Barnard 33, named for the American astronomer Edward Emerson Barnard, who catalogued hundreds of dark nebulae in the early 20th century. Barnard's photographic plates of the Milky Way revealed for the first time that many of the dark patches in the sky were not empty gaps, but obscuring clouds. Before Barnard, many astronomers believed that the dark patches in the Milky Way were simply regions where there happened to be no stars. It was Barnard who first showed convincingly that they were instead clouds of dust and gas, blocking the starlight beyond. The discovery added an entire new category of object to the cosmos. The Horsehead is part of a larger molecular cloud known as the Orion B complex, which contains many other regions of star formation. It is silhouetted against the bright pink emission of IC 434, a cloud of glowing hydrogen behind it. Without that backlight, the Horsehead would be nearly invisible from Earth. The Horsehead is roughly 7 light-years tall. It has a complex internal structure of cold gas and dust, with embedded young stars hidden in its depths. Infrared telescopes can see through the dust to the warmth of these young stars, even though visible light cannot. To the naked eye, the Horsehead would look the same 1,000 years from now. To infrared, it would look quite different. The Horsehead is also slowly being eroded. The bright young stars that light up the surrounding emission cloud are also irradiating the dark cloud's edge, slowly stripping it away. In another 5 million years or so, the recognizable horse shape will be gone. The dark cloud will continue to exist, but in a different form. Far in the southern sky, in the constellation Crux, lies another famous dark nebula, the Coal Sack. It is a large, irregular dark patch beside the Southern Cross, easily visible to the naked eye even from suburban skies. Many ancient cultures observed and named the coal sack long before they knew what it was. The Inca, the Aboriginal Australians, and many other Southern Hemisphere peoples included the coal sack in their celestial mythologies. To the Inca, it was an emu in the sky, with the Southern Cross as part of the bird's body. The dark patches of the Milky Way, taken together, form an emu shape that predates many other named figures. In the constellation Ophiuchus lies the Pipe Nebula, a long curving dark cloud that resembles the silhouette of an old smoker's pipe. The pipe is part of the Ophiuchus molecular cloud complex, one of the closest active star-forming regions to Earth. Inside its quiet bowl, new stars are slowly gathering. Nearby, the Snake Nebula, Barnard 72, slithers across the sky in another distinctive dark shape. The snake is much smaller than the pipe, but no less recognizable. Within its winding form, dense molecular gas is patiently doing the slow work of star formation, hidden from any visible light view. Some dark nebulae form especially small, dense, isolated knots known as Bok globules. They are named after the Dutch-American astronomer Bart Bok, who first proposed in the 1940s that these objects were the cradles of new star formation. He turned out to be entirely correct, although it took decades for his hypothesis to be confirmed. A typical Bok globule is about a light year across, with the mass of a few dozen suns. Inside, the cold molecular gas is contracting under its own gravity, slowly heading toward the formation of a star or small cluster of stars. They are some of the most direct examples we have of the early stages of stellar birth. The Thackeray's globules in the IC 2948 cloud are another famous example. They were photographed beautifully by the Hubble Space Telescope, appearing as dark teardrops scattered across a bright pink background. Each globule is independently doing its quiet work. Inside dark nebulae, the gas is unusually cold by cosmic standards. Temperatures can drop to 10 or 20 degrees above absolute zero, about 250 degrees below freezing on the Celsius scale. At such low temperatures, hydrogen atoms can pair up into hydrogen molecules, and many other simple molecules can form on the surfaces of dust grains. The molecules that form in dark nebulae include carbon monoxide, water, ammonia, formaldehyde, methanol, and many others. Some are precursors to amino acids and other organic compounds. The chemistry of the cold cosmos is far richer than was once believed. The dark, quiet places of space are also some of the busiest chemistry laboratories. Astronomers study the chemistry of dark nebulae using radio telescopes, since most molecules emit and absorb radio waves at characteristic frequencies. By scanning the radio sky, we can identify which molecules are present in a given cloud and in what abundances. The results have been remarkable. Even amino acid building blocks have been detected. These cold, dark, chemistry-rich clouds are the eventual sources of new planetary systems. When a star forms inside such a cloud, the leftover gas and dust become its planet-forming disk. The molecules and grains that surrounded the star at birth become the raw material of any planets that follow. Our own solar system began this way. There is something deeply soothing about a dark nebula. It does not glow. It does not announce itself. It simply waits, sometimes for tens of millions of years, until conditions are right for the slow gathering of stars to begin. Patience on this scale becomes its own kind of beauty. Most of the dark patches you see in the band of the Milky Way are exactly this: vast, slow clouds of cold gas and dust hiding their interiors from visible light. The galaxy is not nearly as bright and shiny as it looks. Much of it is silent, much of it is dark, much of it is doing its slow work without any need to glow. In future telescopes, we will see deeper into these dark nebulae than we ever have before. Each new generation of infrared and submillimeter instruments has revealed more of what was hidden. Each generation of children grows up with a new picture of what the dark places of the cosmos contain. The dark, it turns out, has been full all along. When you look at the bright band of the Milky Way, you may notice a long dark lane running through it. This is the Great Rift, a series of overlapping dark nebulae stretching for thousands of light years along our view of the galactic disk. It is not a gap in the stars. It is a vast, slow river of cold dust that obscures everything behind it, draped across the brighter band like an old shawl. Edward Emerson Barnard's Catalogue of Dark Nebulae, published in 1919, contained over 300 entries. Each dark cloud was given a Barnard number. Some, like Barnard 68, are now famous in their own right. Barnard 68 is a small, isolated dark cloud in the constellation Ophiuchus, perfectly silhouetted against a dense background of stars, almost spherical, like a perfect drop of cosmic ink. Dark nebulae cannot be detected directly by visible light. To trace their structure, astronomers observe the radio emission of carbon monoxide molecules, which form abundantly in cold, dense gas. The carbon monoxide acts as a tracer for the hidden molecular hydrogen, which is far more abundant but very difficult to detect on its own. Through this indirect observation, the dark places gradually become readable to careful instruments. Some of the dust in dark nebulae is transparent at infrared wavelengths. By observing in the infrared, telescopes can see straight through the obscuring cloud to the stars and forming protostars within. The cold, dark places are not actually impenetrable. They simply require the right kind of vision. With infrared eyes, a dark nebula becomes translucent, almost like fog seen with a long, warm lamp. For much of astronomical history, dark nebulae were detected by counting stars. If a region of the sky showed a noticeably reduced density of stars compared to its surroundings, astronomers concluded that something was blocking the view. This statistical method, used extensively in the early 20th century, gave us our first maps of the dark cloud distribution along the Milky Way, drawn slowly, plate by plate. Now we have spent some time in the silent, patient dark places. Let us turn next to one of the most beautiful kinds of nebulae of all, the planetary nebulae, which are the soft, glowing remnants of dying stars. The next chapter takes us to the ring, the helix, and the cat's eye. In the late 1700s, the astronomer William Herschel coined a term that has stuck for over 2 centuries. He called certain small, round, glowing nebulae planetary nebulae, because in his telescope they looked vaguely like the disks of planets. We now know they have nothing to do with planets at all. They are something far more poignant. A planetary nebula is the soft, glowing shroud of a dying sun-like star. When a star similar in mass to our own runs out of hydrogen fuel, after about 10 billion years, it begins to swell. It becomes a red giant, hundreds of times its original size. Eventually, it gently sheds its outer layers into space, leaving behind a small, hot, fading core. The shed outer layers form an expanding bubble of gas around the dying star's core. The hot core, which is now exposed, emits intense ultraviolet light. The ultraviolet light excites the bubble of gas, making it glow. The glowing bubble is what we call a planetary nebula. It is quite literally a star's last calm exhalation. One of the most famous planetary nebulae is the Ring Nebula, Messier 57, in the constellation Lyra. Through a small telescope, it appears as a pale gray ring of mist, almost like a smoke ring suspended in space. Through a larger telescope, the central white dwarf becomes visible inside the ring, the dying core of the original star. The Ring Nebula lies about 2,000 light-years away. Its expanding shell of gas is approximately 1 light-year across, expanding at roughly 20 kilometers per second. At that rate, the entire visible structure has been forming for around 6,000 to 8,000 years. By cosmic standards, the ring is very young. In the constellation Aquarius lies the Helix Nebula, NGC 7293. The Helix is one of the closest planetary nebulae to Earth, lying only about 650 light-years away. It is also one of the largest in apparent size, spanning about half the apparent diameter of the full moon in the sky. The Helix is sometimes called the Eye of God, because in long exposure photographs it strongly resembles a great cosmic eye with a colored iris around a dark central pupil. Despite the dramatic name, it is simply a quiet planetary nebula at a relatively close distance, presented to us at a beautiful angle. Inside the helix, fine cometary structures called knots have been observed by the Hubble Space Telescope. Each knot is a small, dense cloud of gas with a long, faint tail pointing away from the central star. There may be tens of thousands of these knots within the Helix Nebula alone, like a slow-moving cosmic snow. The Cat's Eye Nebula, in the constellation Draco, is one of the most structurally complex planetary nebulae known. It lies about 3,300 light-years from Earth. Hubble images show it as a series of nested shells, jets, knots, and intricate filaments. Astronomers believe its complexity may result from a binary star at its center. The Hourglass Nebula, in the constellation Musca, has the elegant shape of a tilted hourglass viewed in 3 dimensions. 2 great lobes of gas extend in opposite directions from the central white dwarf. The shape suggests that the dying star's outflow was channeled by some surrounding structure, perhaps a dust ring or a binary companion. The Dumbbell Nebula, Messier 27, in the constellation Vulpecula, was the first planetary nebula ever discovered in 1764 by Charles Messier himself. Its shape, a sort of bow tie or apple core, gave it its name. The dumbbell remains a popular target for amateur astronomers, easily visible through small telescopes on summer nights. The Owl Nebula, Messier 97, in the constellation Ursa Major, gets its name from 2 dark patches that look like the eyes of an owl staring out at the observer. The owl is faint but accessible to medium-sized amateur telescopes, especially under dark skies. The Saturn Nebula, NGC 7009, in the constellation Aquarius, takes its name from the planet Saturn because it has 2 faint extensions that resemble the planet's rings. It was discovered by William Herschel in 1782, just 3 years before he discovered the planet Uranus. Some planetary nebulae have spiral structures, suggesting that the dying star's mass loss was modulated by the orbital motion of a binary companion. Others have point-symmetric jets that have changed direction over time, perhaps because the binary's orbit has precessed. The variety of shapes is enormous, and each tells a slightly different story. A planetary nebula does not last very long. In cosmic terms, the expanding gas shell becomes thinner and fainter over time. After about 10,000 to 50,000 years, the shell will have dispersed enough to be effectively invisible. The central white dwarf will continue to slowly cool over billions of years, but its glowing wrapper will be long gone. Compared to the lifetimes of the parent stars, billions of years, the planetary nebula phase is brief, almost instantaneous. The stars we see as planetary nebulae today have been quietly burning for billions of years and will spend their final tens of thousands of years gently exhaling before settling into a long white dwarf retirement. Our own sun will eventually go through this process, although not for another 5 billion years. Long before that, the sun will swell into a red giant and engulf the inner planets. Eventually it will shed its outer layers, briefly becoming a planetary nebula, and leave behind a small white dwarf core that will quietly cool over the rest of cosmic time. Most of the heavy elements in the universe, most of the carbon in your body, for instance, were produced inside stars during the red giant phase and gently spread into space during the planetary nebula phase. When you breathe, the carbon in your breath has been through this process many times before. Each atom is in some sense a survivor of an ancient, gentle ending. Planetary nebulae are returning material to the galaxy in this slow, gentle way. Their quiet exhalations enrich the interstellar medium with carbon, nitrogen, and oxygen. Future generations of stars and planets will be born from this material. Our own solar system formed from the gentle remnants of such returns, billions of years ago. Looking at a planetary nebula photograph is, in a way, looking at one of the most peaceful endings in the cosmos. There is no violence here. There is no explosion. There is only a soft, expanding shell of gas, a glowing remnant, and a slowly cooling core. The star has not vanished. It has simply quieted. In contrast to this gentle ending, some stars finish their lives in a far more dramatic way. The most massive stars do not become planetary nebulae. They explode as supernovae, briefly outshining entire galaxies and leaving behind very different kinds of remnants. Tonight we will visit some of those next. The Boomerang Nebula, in the constellation Centaurus, holds a strange distinction. Its expanding gas is the coldest natural place ever measured in the universe, only about 1 degree above absolute zero. The expansion of the nebula is happening so rapidly that the gas cools below the temperature of the cosmic microwave background itself. The dying star at its center is, in a sense, refrigerating its own surroundings as it slowly fades. The Eskimo Nebula, NGC 2392, in the constellation Gemini, gets its name from the appearance of a parka-wrapped face when seen in earlier telescopes. With more detailed Hubble imaging, the resemblance becomes less direct, but the popular name has stuck. The Eskimo lies about 3,000 light-years away, with delicate inner and outer shells around its central white dwarf, layered like a cosmic onion. When a star similar to our Sun reaches the late stages of its life and begins to lose its outer layers, the process is shaped by what astronomers call common envelope evolution. If a binary companion is present, the companion can stir the outflowing gas into spirals, lobes, and helical patterns. Many of the most strangely shaped planetary nebulae are now believed to be the work of unseen binary stars dancing slowly together. Before becoming a planetary nebula, a sun-like star spends time on the asymptotic giant branch. During this phase, the star pulses, swelling and contracting on timescales of years to decades. With each pulse, it sheds a thin shell of material into space. Over thousands of years, these accumulated shells become the rich, layered structures we eventually see in the planetary nebula photographs, like rings around a tree. At the heart of every planetary nebula sits a tiny white dwarf, the dense remaining core of the original star. A typical white dwarf has roughly the mass of the Sun packed into a volume the size of Earth. Despite their teeniness, white dwarfs continue to shine with leftover heat for billions of years, slowly cooling into invisible black dwarfs many trillions of years from now, in a future none of us will see. Now we have spent time among the soft, glowing wrappings of dying small stars. Let us turn next to the loud goodbyes of the large stars, the supernova remnants, which are some of the most violent and beautiful objects in our sky. The next chapter takes us to the Crab and the Veil. When a star much larger than the Sun reaches the end of its life, it does not gently shed its outer layers. Instead, its core collapses suddenly, and the rebound shock blasts the rest of the star outward in a brilliant explosion. For a few weeks, a single supernova can outshine an entire galaxy. What remains afterward is called a supernova remnant. Tonight, we will spend some time with the gentle aftermath of these violent events. Although the explosions themselves are sudden and brief, the remnants left behind expand slowly across thousands of years, becoming some of the most intricate and beautiful nebulae in the sky. The most famous supernova remnant is the Crab Nebula, Messier 1, in the constellation Taurus. It lies about 6,500 light-years from Earth and was the first object catalogued by Charles Messier in 1758. The Crab is the visible aftermath of a supernova that exploded in the year 1054 AD. The supernova that produced the Crab Nebula was witnessed and recorded by Chinese astronomers nearly 1,000 years ago. They described a guest star that appeared in the sky in 1754 and remained visible during daylight hours for 23 days. It was so bright that it cast shadows on the ground at night. The Chinese records, along with confirming observations from Japanese, Arab, and possibly Native American sources, allowed modern astronomers to determine the precise date of the explosion. The match between the Crab Nebula's expansion rate and the historical date is one of the most beautiful confirmations in observational astronomy. Inside the Crab Nebula, near its center, lies a tiny, rapidly spinning object called the Crab Pulsar. It is the collapsed core of the original star, a neutron star only about 20 kilometers in diameter, but with the mass of about 1.5 suns. It rotates 30 times per second, sending out beams of radiation that we observe as regular pulses. The Crab Pulsar's energy continuously powers the surrounding nebula. The blue glow at the heart of the Crab is synchrotron radiation, light produced by electrons spiraling at near light speed in the pulsar's magnetic field. This is why the Crab continues to glow long after the original explosion. The pulsar at its center is still feeding it energy. The Crab Nebula has been studied in every wavelength from radio to gamma rays. It is one of the brightest objects in the sky in many of these wavelengths. Astronomers use it as a standard reference for calibrating instruments. The brightness unit, known as the Crab, is named in its honor. In the constellation Cygnus lies another beautiful supernova remnant, the Veil Nebula. It is the visible remnant of a supernova that exploded between 5,000 and 8,000 years ago. Today, its expanding shell forms intricate, lacy filaments stretching across nearly 3 full degrees of sky. The veil is sometimes called the Cygnus loop when referring to the entire roughly circular structure of the remnant. Different portions of the loop have their own names: the Western Veil, the Eastern Veil, Pickering's Triangle. Together they form a single great expanding shock wave that has been moving through space for thousands of years. In the constellation Cassiopeia lies Cassiopeia A, the remnant of a supernova that exploded around the year 1680 AD. Curiously, no records of this event survive from the time. Either the explosion was hidden by intervening dust, or it occurred at an unusual time when astronomers happened not to notice. Cassiopeia A is one of the brightest radio sources in the sky outside our solar system. It is also a strong source of X-rays. Its expanding shell glows with the heavy elements forged inside the original star and ejected during the explosion. The pattern of those elements provides a kind of forensic record of how the star died. Tycho's supernova remnant is the visible aftermath of a supernova observed by the Danish astronomer Tycho Brahe in 1572. This was a type Ia supernova, which is a different mechanism than the core collapse type that produced the Crab. Type Ia supernovae occur when a white dwarf in a binary system gathers too much matter and undergoes runaway thermonuclear ignition. Type Iaa supernovae are particularly important to modern astronomy because they all explode with very nearly the same intrinsic brightness. By measuring how bright they appear from Earth, astronomers can determine their distance with high precision. This is one of the main tools used to measure the expansion of the universe. Kepler's supernova, observed by Johannes Kepler in 1604. It was the most recent supernova in our own galaxy, whose initial explosion was definitely observed from Earth with the naked eye. We are perhaps overdue for another nearby galactic supernova. Recently, in 1987, a supernova was observed in the Large Magellanic Cloud, a satellite galaxy of our own Milky Way, known as SN 1987A. It was the closest supernova observed in over 400 years. Its remnant is now expanding visibly year by year, providing a real-time record of how a young supernova remnant evolves. The supernova remnants are responsible for distributing many of the heavier elements throughout the galaxy. Iron, calcium, and many other elements heavier than helium are forged inside massive stars and then scattered into the interstellar medium when those stars explode. The iron in your blood was made inside a star that exploded long before our solar system was born. In particular, the iron, nickel, and other heavy metals on Earth and in our bodies came from supernovae that exploded perhaps 5 to 10 billion years ago, somewhere in the region that became our solar system. Without those ancient explosions, there would be no rocky planets, no metal-rich crust, no iron in the hemoglobin of our blood. The expanding shock wave from a supernova remnant can also trigger the formation of new stars. As the wave passes through nearby molecular clouds, it compresses them, helping gravity overcome their internal pressure. New stars sometimes begin to form in the wake of an old star's death. The end of one star can be the beginning of others. It is believed that our own solar system may have been triggered, in part, by exactly this kind of nearby supernova. Certain isotopes preserved in ancient meteorites suggest that the cloud which formed the Sun and planets received material from a supernova explosion shortly before the system began to assemble. So, whenever you see a supernova remnant, the Crab, the Veil, Cassiopeia A, or any of the others, remember that you are looking at one of the great recycling moments of the galaxy. A star has died, its substance has returned to the wider cloud. New things have begun somewhere in the wake of its ending. The universe is patient with grief. The Crab pulsar is a particular kind of object called a pulsar wind nebula. The rapidly spinning neutron star at the center sends out a steady wind of high-energy particles, and that wind continuously inflates and energizes the surrounding gas. Every pulsar wind nebula is, in a sense, alive with the activity of its central engine glowing not just from the original explosion, but from continuous fresh input from within. Through history, only a handful of supernovae have been observed in our own galaxy with the naked eye. The most famous are the supernovae of 1054, 1181, 1572, and 1604. Each was a profound event in the cultures that recorded them. Tycho Brahe and Johannes Kepler each observed one in their lifetimes, and each used the observation to challenge older ideas about an unchanging celestial sphere. The Vela supernova remnant is the visible aftermath of a supernova that exploded between 10 and 20,000 years ago in the southern constellation Vela. The remnant covers a vast area of sky and contains a young pulsar still spinning at its center. Vela was one of the first supernova remnants in which a pulsar was identified, providing important evidence for the connection between supernovae and neutron stars. Some of the most extreme stellar deaths produce gamma-ray bursts, brief flashes of high-energy radiation visible across the universe. These are believed to occur when the most massive stars collapse directly into black holes, and the resulting jets sometimes happen to point toward Earth. They are rare, but they connect supernova remnants to a much wider story of stellar endings, from quiet to extreme. The supernova explosion is also the place where many of the heaviest elements in the universe are produced. In the rapid neutron capture process that occurs during the explosion, atoms briefly capture many neutrons at once, forming exotic heavy nuclei. As these nuclei decay, they leave behind elements like gold, platinum, uranium, and thorium. Every gold ring carries within it the silent memory of an ancient supernova event. Now we have spent some time with the loud goodbyes of the most massive stars. Let us turn finally toward the great cosmic cycle that ties all of these stories together. How nebulae make stars, how stars make heavier elements, how those elements return to nebulae, and how each generation of cosmic chemistry enriches the next. Tonight we have visited many kinds of nebulae, the bright glowing emission clouds, the soft blue reflection nebulae, the dark patient dust pillars, the gentle planetary shrouds of dying small stars, the intricate expanding shells of supernova remnants. Each of these is a stage in a vast, slow cycle that has been turning since the universe began. The cycle begins with hydrogen, the simplest and most ancient element. After the great beginning of the universe, the first nebulae were made almost entirely of hydrogen and helium, with very little of anything else. Inside those first clouds, the first generation of stars was slowly born. We call them population 3 stars. The population 3 stars no longer exist. They were almost certainly very massive, and their lives were correspondingly short. Within just a few million years of their formation, they ended in supernovae, scattering the first heavy elements they had forged into the surrounding gas. The universe was no longer pure hydrogen and helium. The next generation of stars, called Population 2, was born from this slightly enriched material. They contain tiny amounts of carbon, oxygen, and other heavier elements. Many Population 2 stars are still alive today, mostly in the dense central regions and the outer halo of our galaxy. They are some of the oldest objects in the universe. After many cycles of star birth and stellar death, the interstellar medium grew steadily richer in heavier elements. Carbon, oxygen, nitrogen, silicon, magnesium, iron, all of these accumulated generation after generation. Eventually, in some regions, there was enough heavy material to form rocky planets like Earth. The third generation of stars, called Population 1, formed in this enriched material. Our Sun is a Population 1 star. It contains traces of every element that earlier stars produced. The matter that makes up our world, our bodies, and everything we touch was enriched by perhaps 3 or 4 cycles of stellar life and death before it found us. Carbon was made primarily inside the cores of red giant stars. When those red giants reached the end of their lives and gently shed their outer layers as planetary nebulae, the carbon was returned to the surrounding cloud. The carbon in your DNA, in your skin, in every breath you exhale, was once inside a long-vanished red giant. Oxygen was made in the cores of more massive stars, and in the great explosions of supernovae, each oxygen atom in the water you drink, in the air you breathe, in the molecules of every living cell, was forged inside a massive star that lived and died long before our solar system existed. The iron in your blood, the iron in the structure of every red blood cell, the iron in the steel of cities and cars and buildings was forged in the final stages of massive star evolution and scattered to space by supernova explosions. Without those explosions, there would be no iron on Earth and no oxygen-carrying blood in our veins. Even heavier elements, gold, silver, platinum, uranium, were forged in even more violent events. Recent observations have suggested that many of the heaviest elements in the universe were produced by the collisions of neutron stars, the densest objects known. Each piece of jewelry, each electronic component, carries an inheritance from one of the most extreme events in the cosmos. Calcium, the element of bones and teeth, was made primarily inside massive stars. When you stand up, when you bite into food, when you walk across a room, you're using elements that were once inside the cores of stars, far more massive than our Sun. The fact that you can stand at all is a souvenir of a long-vanished cosmic furnace. Each new star formed in the modern Milky Way galaxy has more heavy elements than its predecessors. The galaxy has been slowly enriching itself for billions of years. The latest generation of stars now forms in clouds that are perhaps 2% heavy elements by mass, small in fraction, enormous in importance. Looking out into deep space, when we observe distant galaxies whose light comes from the early universe, we see fewer heavy elements there. Those distant galaxies are seen as they were billions of years ago, before the great enrichment had progressed as far. The distant universe is, in chemical terms, younger. This great cycle of nebulae and stars and supernovae and recycling has shaped not just chemistry but the whole geography of galaxies. The arrangement of stars and dust in our spiral arms, the location of star-forming regions, even the eventual evolution of galaxies into older quiescent forms, all of these are influenced by the slow turning of the cycle. In time scales much longer than our human lives, The cycle slows as more and more material is locked into long-lived white dwarfs and neutron stars and black holes. Less remains in the interstellar medium for new stars. Eventually, the era of star formation will end, but that ending is many tens of billions of years in the future. Astronomers estimate that the great age of star formation in our galaxy is now past its peak. Our Milky Way is forming new stars at a slower rate than it did several billion years ago. We live in an era when the cosmic furnace is still bright, but slowly cooling. We are partway through a long, quiet evening of cosmic history. Looking forward, in many tens of billions of years, the era of stars will give way to the era of red dwarfs, the smallest and longest-lived kind of star. They will burn slowly for trillions more years. Eventually, even those will fade. The universe will enter a long, dark, quiet phase of slowly cooling stellar remnants. That is many trillions of years from now. We are living in a moment when the night sky is rich with bright young stars, glowing nebulae, and active galaxies. Our era is, by cosmic standards, dazzling. Future witnesses, if any exist, will see a much quieter sky. We are in good time tonight. Each breath you take pulls in oxygen molecules made inside dying massive stars. The water you sip carries hydrogen from the dawn of time and oxygen from supernova explosions. Your bones contain calcium from cosmic furnaces. You are, in a literal and chemical sense, made of the slow patience of stars. Tonight, while you rest, that long cycle continues. Somewhere in the Milky Way, new stars are being formed in nebula nurseries. Somewhere else, old stars are gently shedding their outer layers as planetary nebulae. Somewhere else, a massive star is in its final hours before exploding as a supernova. The cycle does not stop because it is night, nor does it stop because we cannot see it. Most of what is happening in the galaxy at this moment will not be visible to us for thousands of years, if ever. We are surrounded by slow events whose details we will never witness. The cosmos is patient with our limited senses and continues its work in any case. The earliest universe contained only the simplest elements made in the great beginning itself. There was hydrogen, helium, and a small trace of lithium. There was no carbon, no oxygen, no iron, no calcium. The first true nebulae of the cosmos were therefore very different from those we see today, lacking the heavy elements that color modern emission regions or build modern dust grains. Slowly, generation by generation, the chemistry of the cosmos grew more elaborate. A galactic chemical evolution is the field that studies how the elemental composition of galaxies changes over cosmic time. By measuring the chemistry of stars of different ages, astronomers can reconstruct the history of star formation and supernova activity in a galaxy. The Milky Way's chemical history is now understood in remarkable detail, with each generation of stars leaving its quiet fingerprint in the next, like a slow ledger. Our Sun is generally classified as a population 1 star, formed from material already enriched by perhaps 3 or 4 prior generations. The exact number of generations preceding the Sun is hard to pin down, but at least several major rounds of star birth and death contributed the elements that now make up our solar system. We are, chemically speaking, late in the lineage and grateful for everything that came before us. Looking forward across the truly long span of cosmic time, the era of star formation will eventually end. After many tens of billions of years, the gas reserves of galaxies will be depleted. New stars will become rare, then absent. The universe will enter what cosmologists sometimes call the degenerate era, when only stellar remnants remain. Even those will eventually fade. But all of that lies far beyond any horizon we will ever know. There is something quietly comforting about being part of a cycle that does not end with us. The atoms in your body have been through many slow rounds of formation and dispersal already. They will continue after we are gone into other configurations. A cycle does not end, it only changes its current form. Tonight, in this brief and gentle moment, the form is you, listening, breathing, alive. It has been a long night of cosmic visiting. We have looked at clouds where stars are born, at columns sculpted by ultraviolet light, at glowing emission and soft reflection nebulae, at dark dust-rich shadows, at the gentle exhalations of dying small stars, at the violent and beautiful aftermath of dying massive ones, and at the great cycle that ties them all together. Now it is time to rest. We have come a long way tonight, from the soft pillars of the Eagle Nebula to the glowing veil of a dying star, from the blue reflection clouds of the Pleiades to the ancient ribbons of the Veil Nebula. The universe has shown us only a small portion of itself, and even that small portion has been more than the mind can hold. The nebulae we visited have not noticed us. They will continue their slow work whether we watch or not. New stars will keep igniting in their depths. Old stars will keep returning their material to the great clouds, so that the cycle may begin again. Nothing about tonight has hurried any of them. Nothing about tonight will. Somewhere, light is leaving a nebula right now. It will travel for thousands of years before reaching another world. Perhaps another listener, perhaps no one at all. The universe spends its photons generously, with no expectation of return. Tonight you have received some of them. They were saved up across long ages, just to arrive in this quiet moment. If your eyes are still open, allow them to close now. There is nothing left to see that has not already been shown. The nebulae will be here tomorrow and the night after, and 1,000 years from tomorrow. They are not in any hurry to be witnessed. You can come back any time. They will be waiting, patient as ever. Let the slow rhythm of your breath continue in and out. The cosmos breathes too. In cycles far longer than ours, stars form and stars end, clouds gather and clouds disperse. Galaxies turn and turn. You are part of this rhythm. The atoms in your body once belonged to a nebula. One day, far from now, they will belong to another. Thank you for spending this night with the Circadian Institute. If this journey helped you rest, please consider subscribing. It allows us to keep building these slow, deep visits to the quieter places of the universe. New videos arrive each week, always at this same patient pace, always meant for your sleep. Until we meet again, the stars will keep being made. The dust will keep drifting between them. The light will keep traveling, carrying news of distant beginnings in no rush at all to arrive. The universe is in good hands tonight, and so are you. Good night from the Circadian Institute. Sleep deeply, sleep well. The nebulae are still glowing, the cosmos is still breathing, and tomorrow when you wake, all of this will still be true. Good night.